So in this problem, we're given a situation that looks like this. We have a block of mass m being pulled up a slope of angle theta by a rope with a tension T. Now I'm going to draw an isolation diagram of the block. It's got the force of gravity, mg, pulling it downwards, tension force pulling it up the slope, the normal force pushing it away from the slope, and the force of kinetic friction resisting the force of tension. I'm going to define this to be the positive x direction and this to be the positive y direction. And we're asked first is what is the work done by the block due to gravity if the block is dragged slowly a distance d and then brought back to rest. Now what it means by dragged slowly is that the block does not accelerate during that time. So that's going to be important later on. So in order to find the work due to gravity, I have to take the integral from 0 to d of the force of gravity dot dr. And that's just going to be the integral from 0 to d of mg times cosine of theta plus 90, or theta plus pi over 2, because strictly this should be in radians, times dr. And that's because the force of gravity is pointing straight downward, so we have a 90-degree angle, plus that theta angle right there. So remembering that the cosine of theta plus pi over 2 is just negative sine theta, we get that the work due to gravity, and also that this is a constant, we get the work due to gravity is minus mg d, the distance, times sine theta. Now, for part B, we're asked what the work due to the tension force is going to be, and we're going to do exactly the same thing. We take the integral from 0 to d of tension dot dr is equal to the integral from 0 to d of t cosine, and this time it's the angle from this to the dr is pointing in the same direction, so that's just going to be the cosine of 0 dr. So we get that's equal to t times d, and now we need to find the tension force. So the tension force, since the block is not accelerating, is just going to be equal to mg sine theta plus the force of friction. So it's d times mg sine theta plus uk times n, which is equal to mg sine theta plus mu k mg cosine theta, since that's going to be the normal force, times d. So that is the work due to the tension force. Now finally for part C, we're asked what the work due to the frictional force is going to be. And once again, we're going to take the integral from 0 to d, this time of the friction force dot dr, and this is going to be mu k mg cosine theta times d, and now we need to find the cosine of the angle between the friction force and dr, which is just going to be -1 because the two are pointed in exactly opposite directions. So we're just going to add a negative there, and so that's going to be the total work due to friction. So now, finally for part D, we're asked what the net work done on the block is over this distance d. So all we have to do to find that is sum up these three works. The normal force won't do any work because it's always pointing orthogonally to the direction of motion, which means the cosine of the angle between them is going to be 0. So if we add all these together, we get mg sine theta times d minus mg sine theta times d plus mu k mg cosine theta times d minus mu k mg cosine theta times d, and we get that the net work is 0. Now this makes sense because the block starts at rest, is pulled slowly up the ramp, and then is brought back to rest at the end. So the total change in kinetic energy is 0. And we know that the net work, according to the work-energy theorem, is the change in kinetic energy. So if the kinetic energy stays the same from beginning to end, then the net work over that time also has to be 0.